Welcome back to the office. We want to take a look at a couple of theorems. Actually, one of them is given as a corollary, which I find a little bit interesting because in reality, probably both of them should be listed as corollaries rather than corollary and theorem here. So first we have that every group of prime order must be cyclic. That's pretty interesting. And it's a pretty simple example in light of Lagrange's theorem. So if we let G be a group, so this is going to be most of the theorem, just lacking in the nice format. Sorry, most of the proof, just lacking in nice format. Let G be a group such that the order of G is P a prime. Excellent. And we want to let, I don't know, G be in the group G such that G is not the identity, right? Because the group or the subgroup generated by E is just E, right? It's just the identity. Then, according to Lagrange's theorem, the order of the subgroup generated by G must divide the order of the group G. That is, the order of the subgroup G is equal to some multiple of the order of G, which is equal to, I'm sorry, I wrote that backwards. G, the order of G, must be written as some multiple of the order of the subgroup. There we go. But this is P a prime number. So the order of G must be equal to 1 or P. But we know that the order of the subgroup generated by G is not 1, since G is not the identity. Therefore, G is generated by G. So G must be a cyclic group. So that's really interesting to see, right? Every group of prime order is cyclic. It must be cyclic. All right. The order of an element of a finite group divides the order of the group. Well, this seems very trivial. So order of an element divides the order of the group. And this is merely recognizing a definition here. Order of an element is the order of the subgroup generated by that element. So since we have that the order of a subgroup divides the order of a group, then since the order of an element is defined to be the order of a subgroup, we must have that the order of an element divides the order of a group. Hence, order of element, which is order of subgroup, must divide the order of the group. Because that's Lagrange's theorem. Okay, here, this is the application of Lagrange's theorem. And that's why these really both should be corollaries of Lagrange's theorem, because they're both immediate results. All right, that's all I wanted to share for this video. What we want to do is we want to take a look at one more idea of the index. So join me for one more video and example regarding index.